Okay. Yeah, I just thought I'd mention some things because they're like a few things that I can imagine wanting to talk about, but don't actually want to talk about because I'm not really prepared.
Sure.
So one thing I've been making a little progress on is this idea of the Legendre transform as a kind of limit of the Laplace transform.
Yeah.
And there are these papers by, I guess, Litvinov and Maslow, where they talk about that idea of the Legendre transform as a tropical, I don't know if they use the word tropical, they'd say idempotent analysis
Sure.
version of the Laplace transform. But when I looked at that stuff again, it was very formal in the sense that like there's a lot that could be fleshed out to really make it make sense completely. But so I realized that I understood that stuff less well than I would like. And then I discovered that in physics, that idea is actually used somewhere. Namely,
Just a general idea of Legendre transform as a limited case of Laplace transform?
Yeah. So
I would think it's used a lot of places, but go ahead. Yes.
you do? Okay. Well, like where?
Well, if you just open up a little bit more to include Fourier transform in the picture as well, in imaginary time or something like that, or vice versa, then you're looking at kind of everything. Classical limit of quantum mechanics and the WKB method, and but in imaginary time, maybe with statistical mechanics and the temperature. I mean, the way I think of it is that the low temperature is a the limiting case of low temperature is limiting case of low temperature statistical mechanics is sort of classical statics. That's the way I think of it. Yeah. But that's not the way most people think of it. There's lots of ways to think about this. But go ahead. Yeah.
Yeah. So I mean I picked up that from you, the low temperature limit approach.
Yeah.
But of course, yeah. So anyway, physicists don't use that much, mainly because there isn't a whole lot of exciting stuff that gets them. I mean, maybe there would be if they did it the right way, but they're not.
Yeah.
It's there's just not a lot of statistical mechanics problems where you want to take the temperature goes to zero limit and then like dual and then say, oh, it's classical statics. It's just, I mean, it's too easy or something. So
well, that's why I like it, because it's too easy.
Yeah, but anyway, so it turns out that there's like another place where they use this stuff in statistical mechanics where it really seems to be doing something more for you. And it turns out that it's a common thing and I'd never heard about it. So the rough idea, very rough idea, is that you're looking at the, sorry, let me try to figure out here. Yeah, there's a formula for the partition function in terms of a Laplace transform, and then the logarithm of the partition function is called the free energy, approximately. And then they take a certain limit where that Laplace transform turns to a Legendre transform. And in this limit, they express the free energy in terms of the, sorry, this sounds so technical, but in terms of the microcanonical entropy, the entropy where you like constrain the energy to a particular precise value. And so they take the Legendre transform of that microcanonical entropy and get the free energy out. But I'm not trying to explain this. So
again, I'm having trouble seeing the difference. I mean,
so the big difference is that it's not a low temperature limit. Interestingly, it's
okay. Well, okay, but it's still the free energy. The free energy is the same thing. But anyway, keep on going.
Yeah, so it's a limit where the system becomes very large in a certain way. So it's some kind of, I guess they would call it like sometimes a thermodynamic limit, like an infinite volume limit. And it's very funny how they do it.
This is very interesting, but it's still sort of the same thing. But go ahead.
Well, yeah, sure. Everything is the same thing. Yeah. I mean, you could try to you can mess around with these limits in various ways, and you could try to reinterpret the large volume limit as a low temperature limit.
That's right, because it's just the emergence of determinism from indeterminism.
Right. Well, that's what I'm really interested in. So what I'm trying to do is I'm trying to see classical thermodynamics emerging as a limit from statistical mechanics. That's what I want to. That's the way I want to think about it. And so in classical thermodynamics, you have these macroscopic parameters like energy and volume and pressure, and they're deterministically related, and you don't act as if they're like random variables. You act as if they're like sharp variables, and that's supposed to show up. I want that to show up as a kind of limit from statistical mechanics, where when the system becomes very large, the fluctuations are small in comparison to the some kind of law of large numbers type thing, and things become deterministic. And then I want to see the Laplace transform morphing over to the Legendre transform, and that's basically what these guys are doing. But there are a bunch of funny features about it that I want to sort out.
If you go back and look at what Gibbs was originally doing, he was really originally doing all of this.
So how do you go back and look at what Gibbs was originally doing
I don't know. Did I actually read his papers, or did I just read about what he was doing? But I mean, there's this concept of.
Sorry, I'm still here. I'm just invisible.
I mean, it's making me think of Gibbs free energy and stuff like that.
So part of what I was hoping
it's clear I'm just reacting off the cuff here. It could be that there are all sorts of things going on here that I don't understand. Sorry, what were you going to say?
Well, it is true that I do really want to read stuff by Gibbs and Boltzmann and so on, and try to figure out a bunch of things about how they were actually thinking and first.
Right. So, right, a lot of these, well, Gibbs and, I may be naming the wrong person, but I think it's Gibbs and maybe predecessors and followers. But I think Legendre transform is all over his thermodynamics.
Oh, yeah. Well, yeah. Yeah, Legendre transform is used all over the place.
You just kind of have to turn it into, you just kind of have to take what he did and just think of that as this limit of statistical mechanics.
Well, that's what I'm trying to do. Yeah, that's what I'm trying to do. So I know a bunch of stuff theoretically about how Legendre transform is used.
Every time you see Gibbs using Legendre transform, you just try to turn that into a use of Laplace transform in statistical mechanics.
That's what I want to do. Yes, and to do that, you don't really want to. You can argue, but I don't want to think of that as a low temperature limit because what Gibbs is studying is like classical thermodynamics, not at zero temperature, but just at any old temperature. So the physical
sure.
don't worry. Like, I just want to tell you, you're so argumentative. So the more appropriate way to think about the limiting process is probably going to be something like this large volume, large number of something kind of limit.
Sure, but like you say, these are all, these limiting cases are all sort of secretly morally equivalent. They're just, redundancy. I mean, you can think of the low temperature limit as a kind of redundancy limit. But it's determinism through redundancy. That's kind of what you're talking about.
Yeah. So what I want to, so what I'm hoping, one of the things I'm hoping is that it'll be very nice to organize it all in terms of Boltzmann's constant going to 0, because Boltzmann's constant is, on the one hand, like Planck's constant, it's a constant like mathematicians like to set equal to 1 because they think it's like so silly. It's just like a matter of badly chosen.
Other kinds of mathematicians like to do something different, but go ahead. Yeah.
Well, a lot of mathematicians like to set they don't like units, and so they like to set as many constants as possible to 1, unless, of course, they're doing deformation theory, in which they know that you can't do that for the deformation, to let it go.
That's part of it. Yeah, that's a big part of why mathematicians want to recognize those constants.
Yeah. So, but there's some I'm really excited about the relationship of Boltzmann's constant and Planck's constant for all sorts of reasons. So one reason is just a sort of cool historical reason, which is that the first time Boltzmann's constant was ever mentioned was in Planck's paper, in which he introduced Planck's constant, actually. So this makes me more curious to read stuff by Boltzmann, because I don't know what Boltzmann did without, maybe he didn't call it, but I wouldn't call it Boltzmann's constant, but I got the feeling like he didn't even introduce it, maybe he didn't introduce a specific value for it. But the thing about Boltzmann's constant is that cat doing something? Looks like
the cat is certainly doing something.
Yeah. Okay. So okay.
Do you see the cat or do you hear it?
I see the cat, and
you see the cat. Okay.
I see it moving in a way that looks like it's throwing up or coughing up grass, coughing up.
I don't know.
Air. Anyway, but so what's interesting is that Boltzmann's constant is sort of a way of, it's sort of connected like it's very close to Avogadro's, the reciprocal of Avogadro's number. So it's sort of basically
That's
saying
certainly
like
a measure of redundancy. Yes.
Yeah. So how many little things there are in each teaspoon of
or fine graininess, right? I mean,
and so it's very, so in that way it is very similar to Planck's constant, which you can think of like if you've got a laser beam, how many photons are actually in there? It's like 1 over Planck. It's proportional to 1 over Planck's constant. So I'm wanting to really think of those constants now as like the sort of the real and imaginary part, I'm not saying they're the real imaginary part of some constant, but they're like the real imaginary flip sides of this story, just like the Fourier transform and the Laplace transform are flip sides of the same story.
Could you just repeat the last couple of sentences? I kind of missed the.
I'm trying to think of Boltzmann's constant and Planck's constant as like two avatars of the same thing, just like Laplace.
I'm saying sure from the point of view of this is a good thing to try to do, and not that I'm clearly seeing the right way to do it.
So anyway, that's something that sometime I'd like to talk about after I actually get some stuff to work out. It's just working out a little bit. It's just working out a little bit weirder than I had expected. I mean, I would have expected that like this would be all like worked out already, actually, but so that's why it's sort of weird. Well, there's another thing, a completely different thing that's on my mind that I don't know if we've ever talked about. So there's something that we probably did talk about once, I imagine, I don't know, called the threefold way, which is the way that the real numbers, complex numbers, and quaternions all show up when you're studying complex representations of groups.
Do you particularly associate this with, like, I don't know, is Arnold, who came up with the names?
The threefold way actually comes up in a paper by Freeman Dyson. And then Arnold had this paper on trinities, which has some similar themes, but is much more mystical, trying to connect all sorts of threes of all sorts. Okay. Whereas Dyson's is much more of like a coherent story that actually makes sense so far. Whereas Arnold seems to be like grasping for something that hasn't been worked out yet. So the idea, one of the ideas is that, like, if you take an irreducible representation.
But you did say reals, complexes, and quaternions, is what you said?
Yeah.
Okay.
So like one idea is that if you take a irreducible complex representation of a group, there are like three possibilities for what it can be like. So it can be the complexification of a real representation, or it can be the underlying complex representation of a quaternionic representation, or none of the above. And there are lots of so these are but the key thing is that those are mutually exclusive alternatives, so that like it can't be both a complexification of a real one and the underlying rep of a quaternionic one.
I'm very tempted to interpret what you just said in terms of just the idea that real representation theory is more fundamental than complex representation theory.
Right. Yeah. So that's, someone asked me, I was talking about this and someone asked that question. Yeah. So there's another way to say it, which is like, take a real irreducible representation, and then the version of Schur's lemma that you get there says that the transformations that commute with all the group action form a division algebra.
I mean, another way to put it is the study of real two Hilbert spaces is, different from the study of complex two Hilbert. I mean, it depends on how you define what a real two Hilbert space is, but you should probably allow, the Hom spaces. What am I trying to say? Right, you can end up with the endomorphism rings. Right, there's the good concept of a real two Hilbert space allows the endomorphism algebras to be either R, C, or H.
Right. And that sounds good. Yeah, I should think about that. That's a good idea. I've never studied them, but that makes a lot of sense. So there's this idea.
I think it's sort of equivalent to what you're saying. And then when you complexify those real two Hilbert spaces, you get kind of what you're talking about. Yeah.
Yeah. Right. So one funny thing is that, like, you can see this threefold way from real eyes, and you're probably right that that's like the simplest way to look at it. But then you can also see it from complex eyes. That's a really bad pun, but you can so there you see that an irreducible.
Sorry, which pun? Realize?
Complex eyes.
That's not a word, but realize is. Sorry,
right. No. But
I guess I'm missing all the puns. Yeah.
Okay, the square root of -1 is called I.
Okay. Okay.
So all eyes are complex.
Okay, I was thinking this is imaginary. Okay, go ahead.
Yeah. Okay. So you can see it from that point of view, and there, what you do, there, the way it like manifests itself is that if you have an irreducible representation, you can get these anti-linear intertwining operators on it. that are sometimes. So the Schur's lemma says, well, all you get are complex multiples of the identity as complex automorphisms or endomorphisms, but if you allow for anti-linear ones, then it turns out that an irreducible representation can have an anti-linear guy, and you can either have an anti-linear guy that squares to 1 or one that squares to -1. But for an irreducible representation, you can't have both, you can show. And so that's like the way to tell whether like secretly your thing was real, and that this anti-linear operation is complex conjugation, which squares to 1, or secretly it was quaternionic, and then this anti-linear operation is like J or something that squares to -1.
Again, I'm trying to figure out ways to think about it. It sounds like you're saying that when you complexify a real 2 Hilbert space, there's no collapsing of objects or something like that. So that way, whichever one of the 3 colors the basis elements were in the real case, you still get that tricoloring in the complex, in the complexified case, right?
Yeah, I think that may be right. Yeah, one way to think about this tricoloring is that it's a -1, 0, 1 grading. So with respect to tensor product,
yeah, go ahead. Yeah.
With respect to tensoring, these 3 kinds of things act just like the multiplicative monoid -1, 0, 1, which is sort of cool because you usually think of like group gradings, but this is like a monoid grading. So the complex guys eat everyone else, like multiplication by 0 eats every other number. If you like tensor a complex one and a real one, you get a complex one, for example. So that's fun. But anyway, there's like a bigger story, which is called the tenfold way, that is fashionable these days.
Sorry. Which one? Which correspondence you said was the?
Oh, 0 is like complex.
Going from -1, 0, 1. Which are they?
So -1 is quaternionic.
-1 is quaternionic
because J squared is -1, and
J squared
and +1. I'm going to not go in the order you said. And +1 is like real, because complex conjugation squared is +1, and then 0 is complex. And
why?
Yeah, so
just because. Okay, that's fine.
That's unfortunately, that's sort of a weird one.
Well, we'll just have to work it out. But okay,
you could think of it as like you're making up this algebra where you're throwing in an operator J, where J squared equals some real number. And when J squared equals -1, when J squared is negative, this algebra is isomorphic to something, and when J squared is equal to 0, it's very different, and when J squared equals 1, it's again, when J squared is positive, it's very different.
Well, I'll have to think about that, but you always, in these little finite correspondences, you find some glitches, and if you think about it in different ways, they can seem less glitchy and stuff like that. So yes, right. Okay, yeah. That's good enough for now, certainly. Now you started to talk about the tenfold way.
Yeah, there's a thing called the tenfold way, which is basically the super version of this whole story, where instead of like starting out with representations of groups on vector spaces, you look at representations of Z2 graded groups on Z2 graded vector spaces.
Okay.
And so then it turns out that you get interested in these things called superdivision algebras. There's like a super sure lemma.
Well, now you're making me want to think about these super 2 Hilbert spaces, real super 2 Hilbert spaces. Keep going.
Yeah. So that's very interesting. So then instead of 3 different things, there are 10. Um, and it's very, very rich and very beautiful. It's connected to Clifford algebras, and it's connected to what was I going to say? It's connected to the Bott periodicity, and it's connected to.
Sorry, what was the first? You just said Bott periodicity. What did you say before that? Did you say something?
Clifford algebras.
Oh,
so,
but
so
okay.
one way to think about
but that's also part of the same story with Clifford algebras and the Bott periodicity.
Yeah. So it turns out that every super division algebra is Morita equivalent to a Clifford algebra. And so
say that once again. Every what?
every super division algebra, which I haven't defined yet, but they are what show up in the Schur's lemma in the Z2 graded context. Every super division algebra is Morita equivalent to a Clifford algebra. And so they're like 8 Morita equivalence classes of complex Clifford algebras. That's like of real Clifford algebras. That's like the real Bott periodicity 8-fold clock. And then there are 2 Morita equivalence classes of complex Clifford algebras. That's the 2-fold periodic of a complex Bott periodicity. But they both show up together. So
I think the way you said it, and maybe this is the way you said it, that every superdivision algebra is Morita equivalent to a Clifford algebra. You didn't mean to say vice versa.
I meant it to say it the other way around.
You did mean it to say
they're both true, but
the other way around.
What? Yeah, so because they're
The key point is the other way around.
Algebras, but there are only 10 super division algebras, so it's better. It's a more useful thing to say that.
Sure.
So the Clifford algebras keep going on and on. and I mean both the real ones and the complex ones here sort of lumped together. It's the same kind of funny thing where like lumping together the different extensions of the real numbers. They sort of like all get into the act.
All right, but wait. It sounds like you're saying, don't tell me. I mean, are you saying that 3 equals 1 plus 2 and 10 equals 2 plus 8?
Yes. Right. So the first 3 equals 1 plus 2 is about the Brouwer group of the reals is Z mod 2. And the Brouwer group of the complexes is 1. So Brouwer groups, are about
Sure. Well, I mean, I'm saying sure in the sense that sure, that's a good idea. But
yeah, well, it's a good way to sound like you know it. But you're too honest.
Okay. So it is going on here. Okay, so it really is going on here. 3 really is equal to 1 plus 2, and 10 really is equal to 2 plus 8.
Right. So there's a concept of Brouwer group, and then there's a concept of super Brouwer group. But what I'm actually hinting at here, which I've written about a little bit is online, is a Brouwer monoid, where you don't just where you sort of
which unifies
the Brouwer groups of a field and all its algebraic extensions. They fit into a Brouwer monoid. So our reals and quaternions are central simple algebras over the reals. And if you tensor reals and quaternions in any combination, you just get like things that are built up out of the reals and the quaternions. Like
Well, okay.
Quaternion
So
tensor, you never get into the complex stuff that way. But if you tensor either the reals or the quaternions with the complex numbers, you get an algebra that's complex. And that's basically sort of because the complex is like a field extension of the real numbers. And so it's sort of, it's not a central simple division algebra because its center is actually bigger than the reals. So, but
it sounds like you're also saying that 2 = 1 + 1, but I'll have to work that out.
Well, I'm sure it's true. I just don't know what it means. What do you mean by it? Yeah. Yeah. So anyway,
Well, I mean, I'm just saying that there's some monoid homomorphisms here, and there's
a monoid homomorphism
element
from the
monoid and a
non-super
10-element
stuff
monoid.
to
What?
the super stuff. There's a monoid homomorphism from the non-super.
An inclusion homomorphism.
Yeah, that's right. Yeah, so the 8-fold Bott periodicity clock, it has like the real numbers on the top of the clock and the quaternions on the bottom of the clock. And that's like the Z mod 2 sitting inside the Z mod 8. So yeah.
Okay.
So I want to do more stuff with this. A lot. Well, there's stuff I need to learn about this business. There's stuff that I want to clarify about this business. And then there's like, I wish I could like do more with it. And I'm like, one way to do more with it, it's like almost too scary for me, which I did start trying to learn, would be like generalizing this starting from other fields like the rationals. And that's why I started reading that Albert Brouwer Hasse Noether work relating division algebras to over the rationals to Galois theory. But that was really cool, but that's very number theoretic. And I was
okay, but I missed some of what you said because I was writing stuff down.
Yeah,
okay. Go ahead. I mean, not go ahead, but can you
go back
exactly the part I missed?
So I was just saying that I want to figure out some fun things to do in this subject that haven't been done. And so I started looking at how it all generalizes, replacing the reals with some other field like the rationals.
Yes.
And then it's very,
I mean, you already suggested that.
Yeah. Right. Well, you told me to repeat myself. So,
sure, that's fine.
Yeah. So anyway, I was just saying that pulls you quickly into the arms of this work that Albert Brouwer Hasse and Noether were doing, where they were trying to relate division algebras.
Oh, so you really are talking about Adrian Albert or something like that?
Yeah, that's right. So he was actually in with a gang of these otherwise European.
He visited. He went to school in Europe or something.
I don't know. He might have.
I don't know. I don't know. I don't know.
He had some connections to McLean. I mean, he was in Chicago later, and he did talk to McLean. But I don't. And McLean, of course, was at Erlangen, right? Göttingen is what I mean. Yeah. So anyway, but that stuff, while it'd be really fun to talk about with you, probably because you like number theory, and this is like really number theoretic, I was sort of hoping to do some generalizations that were more obviously physics flavored. And so like one direction I was thinking of going was replacing fields like the real numbers with something like C-star algebras, like continuous functions, real valued functions. So you can do this Brouwer group stuff for rings, not just for fields. And so then So then it gets to be sort of like related to vector bundles and stuff. So you can,
Sure, well, sure, that would make sense.
yeah.
But sorry, do people start using the name Azumaya around somewhere?
Yeah, right. Yeah.
Okay.
So Grothendieck was like already thinking about this, but like a sort of algebraic geometry kind of context for commutative rings rather than fields. And so then then the Brouwer group is like has elements that are represented by Azumaya algebras, which just means algebras that have like inverses, tensor product inverses up to Morita equivalence, I guess. Something like that. So yeah, so I've never really quite understood exactly what the algebraic geometers do with this generalization of this stuff to commutative rings. But it's easy to imagine it would be lots of fun. but I was thinking more of like a C-star algebra generalization, just because that's like the kind of algebra that I understand better. And then you might be sort of like if you have like a bundle of group representations, you could maybe sort of repeat this stuff I was talking about, but do it in the sort of fibered way, in a bundly way, and maybe get some topological twists showing up in addition to the usual classification. So anyway, I was just like, I'm looking around for stuff to do about this.
Sure. Can I just a couple of questions here? So I'm trying to figure out what I meant by 1 + 1 = 2. I think maybe what I meant was that sort of at the bottom of something, at the base of something that you're talking about here, there is just a monoid. Maybe you already said this, a monoid of, or the monoid of the algebraic extensions of a given field. And I'm trying to decide what is the monoid operation there and how does it behave and things like that. And I have a feeling that it might be that there are many ways to express this monoid operation. Like almost anything you can think of. As long as it lands back and giving you an algebraic extension, it'll probably be the same. But
the one that I would use, by the way, in this the one that shows up in what I was thinking about was that just the lattice operation on extension.
Well, that's what I'm saying.
Yeah,
that so first of all, it's not just a monoid; it's an idempotent monoid.
Mm-hmm. Right.
Or at least this one that we're talking about is an idempotent monoid.
Right.
And that's just the comment that I want to bring up here, that you have some sort of funny interaction. You're marrying
right
semi-lattices with groups.
Right, exactly. So there's this
which are kind of sort of the opposite extremes in a way.
Right. So there's
all those other kinds of monoids that have sort of slower idempotents, where things don't equal themselves until you start multiplying them together 17 times or something like that. And we're missing out on those here, but maybe we don't want those. But anyway, sorry, I interrupted you. What were you going to say?
Yeah, so the first thing is I wrote on the N category cafe a bunch of things where I showed that like a field will have a Brouwer monoid, where what you do is you first look at the lattice of all the field extensions, and then each one of them gets a Brouwer group. I'm describing it in a way that sounds like it's sort of ad hoc, but but each one has a Brouwer group, and then you can take like the union of all those Brouwer groups, and then there's like a way to make that into a monoid, which sort of
sounds very plausible. I didn't really actually think that all the way through, but it sounds like it makes sense from what you're saying.
Yeah, so it does, and it's So that's nice. And then I
Also
discovered
trying to
this
figure out what
like
that
some
reminds me of.
general,
But go ahead. Yeah, go ahead.
some general theorem about finite. Now I'm very confused, but there's some general theorem about the structure theory of like finitely generated commutative monoids, where there's now it doesn't sound like it seems like you just disproved it by saying that there are these monoids where you have to add something 5 times before you get before it becomes idempotent. But
Well, okay, but maybe I said it wrong. Then let me think.
well,
No, but
there
that's
are.
true. That's true. There are those.
Yeah, but anyway, there's some kind of theory that says that like you can take any finite enough, like finitely generated commutative monoid, and think of it as like sort of being made up out of a lattice. This is probably a bit wrong. I'm forgetting the theorem, but it's something like you can make it out of a lattice and a bunch of groups.
Sorry, what was the epithet you said? Fundamental theorem of finitely generated commutative monoids?
I didn't say that.
What did you
But
say?
it's the structure theorem. A
Structure theorem. Oh, that's the epithet.
Yeah.
Structure theorem.
Like the closest easy thing there is to like a classification of finitely generated commutative monoids. And so it's, it's one of these things where like it's hopeless to completely classify them, but there's still some nice analysis you can do.
Sure.
And so it turns out that it is this kind of interesting, I'll have to look it up again to see exactly how it works. This kind of blend of the sort of idempotent part and the group part. So it's a sort of a general thing to expect when you have a commutative monoid.
I mean, I can't be sure that there isn't some way of blending them, which actually results in something that, allows, maybe that 17 times 17th level of idempotence, maybe that actually does fit into this somehow. I don't know.
I think it has to, because I mean, that's a finitely generated commutative monoid. So there is some, so the theorem handles. Okay.
Right, well,
yeah,
so
I'll just tell you, I'll just say the theorem. I just looked up the theorem. It won't mean anything necessarily, but
okay.
Any commutative monoid decomposes as a semi-lattice of Archimedean commutative monoids. So Archimedean is it's something that means sort of like what people usually mean when they say Archimedean, but it includes it includes groups, I guess. So anyway,
that's suggestive. That's suggestive. Let me just say a little tiny bit about what I meant by 2 = 1 + 1. Did I already say that? So I mean, I'm thinking of 2 = 1 + 1. The 2 is the collection of algebraic extensions of the reals, and equals 1 + 1 equals the reals and the complexes, and that's the base on top of which you get 3 = 1 + 2, and 10 = 2 + 8. So that 10 is, this. Sorry, when you read the theorem, did you say lattice or did you say semi-lattice? Doesn't even matter, but.
The theorem actually winds up saying semi-lattice.
Okay, I prefer that, probably.
Yeah.
That stylistically, linguistically. So yeah, we're saying that, that 10-element monoid in this theorem is, the semi-lattice in all these, the semi-lattice for 10 and for 3 and for 2, those are all the same semi-lattice, which is just the 2. The 2 is just the pure semi-lattice.
Right.
And then on top of that, you're putting these, I guess, you're just getting these semi-lattices of Brauer groups and semi-lattices of super Brauer groups. Yeah. So a lot of the stuff I had never heard of, but a lot of it's making sense. Okay.
That's enough stuff.
Yeah, I think so. I think so.
For me, probably too much, but yeah, so I do want to hear about what, well, you said now you have lots of things to talk about. I didn't want to hear about lots of different things. I would hope to hear about the stuff that we were talking about last time.
Well, yes, but I
I know it's never that
I have
easy.
lots of things to say.
Yep, okay.
And I don't know how well I can manage to say that, but I'll try. So, but first I have to try and find some of these notes here. Should be here somewhere. Okay, so I'm gonna try to go through the list of topics in my notes. You know, some of them are supposed to be very short topics. We'll see how this goes. Okay, so first I should just turn my notebook on, put my notebook on the screen. Is that how this works? Did that show up yet? No, okay. Now it's showing up? Okay.
Yeah, I'll be gone for just 1 second here.
Okay. Sorry, what am I trying to say here?
Okay.
So, okay, so I wanted to start off just kind of very briefly dealing with some alleged sort of puzzles that we've dealt with recently. I just want to give some very preliminary answers to some of the puzzles that we've been dealing with. So one of the puzzles, and I really don't want to talk about this one hardly at all. I just want to say, if I don't even remember the answer, I think the answer was something like f of x equals something like, I don't know what it was, f of x, 4x plus 1 over 4x plus 3 or something like that. It was some Möbius transformation or something like that. And what was this the answer to? This was the answer to, you know, I had this thing about the moduli stack of acute triangles, and sort of, or as a moduli space, sort of coordinatized in a funny way, and it sort of looks like an equilateral triangle itself. And then you have the barycentric coordinates on this equilateral triangle. And so where was this function? Right, let me think of what was the output is supposed to be the barycentric coordinate, and what is the input? I guess it's supposed to be, let's see, maybe this is varying over the upper half plane. I don't even remember, but
I guess as x goes to infinity, this thing goes to 1, which is good. As x goes to infinity, this approaches 1, which sounds like a good barycentric coordinate of like the top of this equilateral triangle.
Yes, I think that's right. Yeah, that's right. So it really is going from the upper half plane to the right. So yeah, it's kind of this Beltrami-Klein projection of you know, the upper half plane is yeah, there's this, it's the hyperbolic plane, you can think of it, but there's this Beltrami-Klein projection to the unit disk, and inside of that we have this equilateral triangle, which you can think of as the moduli space of acute triangles. And yeah, so this Beltrami-Klein projection from the upper half plane, I hope I'm saying that correctly, this Beltrami-Klein projection from the upper half plane to the barycentric coordinates of the yeah, so that's what this is. Sorry, I'm stating that very badly, but this is something we talked about.
Well, actually, what is that? X is supposed to be something you can calculate if you hand me a triangle whose base is like the points something like -1 and 1. And what is x? Is it like the distance from the midpoint of that base to the apex of the triangle?
Oh, I think that's what it was. Is that right? Ah, yes. Okay. Oh, okay. Right. Okay. Yeah, I totally forgotten how this works. That's exactly what that is. Right. It was
Okay.
the distance from the apex. Yes. Thank you for rescuing me there. Yes, that's what X is. X is the
Okay.
distance from the corner that you're interested in to the midpoint of the opposite side, measured in using the opposite side as the unit of length, or maybe it's using the half of the opposite side as the unit of length.
Uh-huh.
It's something like that.
Okay.
And
Yeah.
So I just wanted to state this answer without
remembering what the question was. Okay.
well, right, without even remembering the questions, but yeah.
Yeah.
But,
Uh-huh.
Right.
Okay.
I mean, and right, by not talking about it, I don't want to imply that there aren't, there might be all sorts of interesting, funny things to talk about this, but I'm not going to talk about that anymore.
Okay.
So then we had another puzzle that I talked about last time, which was I sort of tried to fool us into thinking
all right. Yes.
that modular functions are not transcendental.
Yep, you fooled me. Except that I knew it couldn't be true, but you fooled me. Yeah.
Right. Well, so I think, there may be all sorts of interesting things to say about this again, but I'm not going to try to say very many of them. I'm just going to try and give one resolution of the silly puzzle, which is that, so there's this idea that you can start out with an acute triangle. You can build this tetrahedron over it, and this tetrahedron has this Klein-4 symmetry, or this Ferrari-Klein symmetry that I talk about. And again, it has something, right? It's just you take 4 copies of the same acute triangle and you make a tetrahedron out of it in the sort of obvious way. And then you circumscribe a sphere around that.
Uh-huh.
And those 4 points, those 4 corners of this now inscribed tetrahedron so you think of that sphere now as that circumscribed sphere, you think of that as a Riemann sphere now, and you take the cross ratio of those 4 corners of the tetrahedron, and that's just some algebraic function, and it sounds like it's this modular function at level 2 or something like that. But okay, but the basic trick is this, that when you have a tetrahedron inscribed in a sphere like this, there are 2 different ways to get a sphere with 4 points on it from that. One is just take this, circumscribed sphere, and it's got the 4 points right there.
Yeah.
But there's this other way, which is to take the surface of the tetrahedron itself. And, that's got a conformal structure on it. And the conformal structure is just, the normal flat conformal structure on each side, and just at the corners, it just folds out. Sorry, at the edges, it just folds out. And then at the corners, it has this, deficit thing and angle deficit. And, but that gives us, you can just smooth that out kind of, and that gives you, right? So right? That sort of piecewise linear surface of the tetrahedron can actually be, unfolded and smoothed out with, taking account of the angle deficit at the corners. And that gives you a sphere. That is itself a sphere. The surface of the tetrahedron is itself a conformally structured sphere. And that's not equivalent to the circumscribed sphere. So it's the difference between those two four-pointed spheres that's the resolution of the puzzle. They're different.
So are you saying that you got to take the cross ratio with respect to the second one to get the modular function?
Yeah. Which was the second one? Yes. Yes, but yes.
Not the circumscribed sphere.
That's right. That's right. So it's like if you have it's very, very roughly speaking, it's like if you have a a sort of a pool toy that's like shaped like a tetrahedron, but you start overinflating it, and you pump it up so much that it becomes like a sphere. You'll find that as you do that, the corners of the sphere don't just stay in the same relative position to each other. They actually change as you pump it up. I mean, I'm being very sloppy at stating that, but it's true in some sense. And that
for some reason, I'm confused about.
Yeah,
that's interesting. I'm confused about what happens to the angle deficits at these corners. I mean,
yes.
I think I used to understand this.
Well, it's exactly right. It's exactly a 2-to-1 angle deficit, right? I mean, so right. I mean, we're using the same acute triangle for all four sides, and that means that at each corner we're getting all three angles of the triangle showing up. So that is just adding up to 180 degrees, which is exactly half of the 360 degrees that you need. So that's the deficit. And that means that it exactly corresponds to a double cover, that it exactly gets, smoothed out in a sensible way if you do a double cover. I hope I said that right. I mean, I hope you
okay, so I do believe that you get a conformal structure on the double cover of the tetrahedron. That's a nice smooth manifold. But where did the CP1 and the cross ratio go? That is, where did you get the smooth? Where did you get a?
Well, I'm just saying that. That double cover is clearly
that
an
covers
elliptic curve.
CP1.
It's clearly an elliptic curve, and famously, it's clearly an elliptic curve, and those 4 points on it are.
Yeah.
I didn't say that right. I mean, it's clearly the double cover of an elliptic curve, and those those points, that lattice of points, that's the fiber over the two torsion points.
Okay.
Or it's the period lattice, perhaps doubled in scale, and so we know already from having gone to elliptic curve school that there are these elliptic functions that do exactly that they double wrap at each of these two torsion points.
Right. It's sort of weird though, because okay, that I get, but that's sort of funny because like I could take this tetrahedron.
Yes.
And it would have a conformal structure that's nice everywhere except at the corners. And it's topologically a two-sphere, but then there's like this other two-sphere that you define sort of indirectly that has a conformal structure that's nice and smooth everywhere. And for some reason, you get this other two-sphere by taking the double cover of the tetrahedron. And that's got a nice conformal structure. And then you like go back and you map that in a 2-to-1 way down to a CP1. And so it seems like you're like having to do a double cover and then undo it, and then you somehow manage to make these singular points stop being singular.
Well, I mean, there's a general theory of how you can take any piecewise linear manifold in Euclidean space. I mean, certainly, I said piecewise linear manifold. It's probably true, but I'm just thinking of mainly of piecewise linear 2 manifold in Euclidean space. And, it just automatically gets a conformal structure. Just, every time you go over an edge, you just get the conformal structure that comes from unfolding it. And every time you go at a corner, you just work out the angle deficit.
And then, what do you do? I want to know about the corners here. How do you get a conformal structure at the corner?
Do you remember this guy we knew from Usenet, Lee somebody? He told me about this. And he convinced me. So I don't have any good answers to these questions at the moment.
Okay, that's fine. I'm not trying to
I'm hoping that
drag it out, but that somehow it seems I feel like at some point I understood this, but now it seems like a paradox.
Okay, I'm hoping I didn't misunderstand what he said. I thought he said that you just do the sensible thing. You just I mean, maybe you just have to figure out what, maybe you just have to figure out how to define what a conformally structured thing is in terms of angles.
Oh, so maybe at the corners, in this case, you define the angles to be twice what they look like they are?
Something like that, yeah.
Or
whatever, whatever the deficit is, you just adjust.
Well, in this particular case, as you pointed out, it's really nice that at each of the corners, the total angle is half what it should be. So in this particular case,
in this particular case, we don't need a general theory about the piecewise linear things. But
so we could just say, like, at those points, I'll define the angles to be twice what they look like they are.
So right. Okay. I really shouldn't say anything about this, but I have a vague suspicion that there might be, some theory of non-holomorphic modular functions that this might make contact with. I don't know. That's just a silly thought.
Was this Lee Rudolph?
Lee Rudolph. I keep on forgetting his name. Yeah, that's right.
Okay, that's cool. So, I mean, there's all sorts of stuff that we should not get into, but like one of them is like you've shown 2 ways to get a cross ratio from one of these especially nice tetrahedra.
And there's some sort of funny conversion function between those two, but go ahead.
So the question is just like, what's going on? With those 2 functions. But I don't need to.
Okay.
I'm not gripped with the need to answer that.
Okay. So time to go through my list here. So, okay, the next thing that I want to talk about is, and we really are short on time, but that's okay. This is still educational. So the next thing I want to talk about here is, there are these annoying things I've been saying the last couple of weeks occasionally about how, I'm not sure how you usually say it, but I sometimes say something like, well, when we're studying these designs, Grothendieck's designs or when we're studying these designs, there are different ways you can draw them. And there's different different combinatorial tricks that you can play that give you slightly different ways of drawing the designs and working with them. And what often seems to happen is I jump around from one to the other because I suddenly realize I need a different one for reasons of convenience or something like that. And I'm pretty sure that gets annoying because I'm not always making it clear what I'm doing here. So I just want to take a little time here to just describe a sort of grand unified theory of contrasting drawing styles for these designs. And so there's one sort of master drawing style that's sort of the most detailed. I mean, maybe there are even more detailed ones, but yeah, there's one master style that for my purposes is the most detailed. And then all the other drawing styles that we might use on one occasion or another are maybe abbreviations of that, that putting in less detail. Is there another better word instead of abbreviation there? I don't know. But what?
Summary.
But I'm trying to get the idea that it's a visual thing. I mean, it's removing some of the clutter, kind of. There's this very detailed, cluttered thing. So it depends on right? So, on some days you think of it as detail, and it's good, but on other days you think of it as clutter, and you want to get rid of it.
Right.
So let me put in all the detail and all the clutter, and then we'll think about how much you can remove without losing too much information. So, the detailed thing is basically just what I call kind of the irregular Coxeter tile. So I mean, we have this Coxeter group, which is don't tell me. So I guess it's just yeah, it's kind of a Coxeter diagram that looks like that. And I guess I'm thinking of I'm naming the corners by colors, I guess, or something like that. And maybe I should have put that in black. Maybe I should have erased instead of putting it in black. So that's this Coxeter diagram, and if you work out the whole universal Coxeter tiling for that, it's what? It's like it's like, am I doing this right? It's like right. I mean, it's at each corner there's an infinite number of triangles or something like that. So I mean, this is a picture of the group, right? I mean, you can think of these regions as the group elements. Am I doing that right?
Don't you need? Why did you do all infinities? Don't you have like a 3 in here?
Okay, yeah. Sorry. Say that again. What?
Wouldn't this tiling be the universal thing for some Coxeter group that had some finite numbers on its edges, not all infinities?
Finite numbers on its edges.
Like a 3, 4 infinity one or something instead of an infinity. Like,
well, there's a 2, 3. There's a 2. Right. There's a lot of confusing relationship. There's this 2, 3 infinity one that you get by barycentrically subdividing these here. The barycentric subdivisions of this would have these finite numbers, but this thing at every corner. So, right. I mean, sorry. I mean, what I really should have done is I really should have put in, the green there, the blue there, and the red there, and then maintain this, consistent coloring. So there's, that red reflects close to that red, and this blue reflects across to this blue, and that green reflects across to that green. So all these cusps, they all have consistent colorings, and it really is, you know, at the blue cusp there's an infinite number of things, at the green cusp there's an infinite number of things, at the red cusp there's an infinite number of things. So it really is this diagram, and this really is what the designs are based on. You know, there's this different one where, you, like I say, you barycentrically subdivide it, and you know, then you have smaller tiles, and then you know, and then there really is, you know, like a sort of a 2 over here and a 3 over here and an infinity at the cusps or something like that. But that's a different Coxeter diagram. That's really interesting too. I mean, that's the modular group or something like that, or the extended modular group as the extended modular group as the reflection group, and the modular group as the rotations. But here we've got, you know, this Coxeter group as the reflection group, and the rotations is the free group on 2 generators. So, you know, there's this funny relationship between the free group on 2 generators and the modular group. And they're sort of...
I'm confused about why this Coxeter group...
Maybe I'm screwing up. Go ahead, yeah?
Why does this Coxeter group giving us a picture that has triangles in it? What's 3-ish about this Coxeter group? Shouldn't it be giving us infinity gons?
Don't tell me. Well, there's something very 3-ish about it. Look at it.
I know, yeah.
That's it. Right. I mean, there's so every Coxeter tiling is made out of Coxeter simplexes. So the triangles are just framed as the simplexes here. And
okay. Never mind. Yeah, so there are infinity gons, but they're triangulated.
Oh, yes. Oh, yeah, yes. Yeah, oh, yeah, yes, there certainly are infinity gons, but right, part of the problem is that if you want to think in terms of a gon tiling, then you right, you tend to need a straight line Coxeter diagram. This is not a straight line Coxeter diagram. This is a circular, a cyclical Coxeter diagram. So that makes it more uncertain to me how to think of this as a tiling by infinity gons or something like that. Maybe there is some way to think of it as a tiling by infinity gons, but I don't particularly expect that because of the fact that this is not a straight line Coxeter diagram.
Okay, yeah, well, I'm confused. Yep, okay. Okay.
So yeah, there is a general theory of Coxeter groups, and they're Coxeter tilings, and then the irregular Coxeter tilings, which come from, you know, wrapping these up. So, or algebraically, they just come from taking a subgroup of the Coxeter group. And, you know, a subgroup gives you a transitive action, and that transitive action becomes an generally irregular tiling. Whereas, you know, if the subgroup happens to be normal, then then this wrapped up Coxeter tiling ends up being a regular tiling of some sort. So there's this general theory of Coxeter groups, Coxeter tilings, regular Coxeter tilings, irregular Coxeter tilings. There's a general theory of that, which is very nice. And I'm sort of pretending that you and me understand all of that. You know, let's pretend that we already understand that. And given that, you know, I'm doing this example and saying how, you know, Grothendieck's theory of designs fits into this formalism of Coxeter tilings.
Yep.
And so, yeah, so you can define a design, roughly speaking, as being an irregular Coxeter tiling for this particular Coxeter diagram, this particular Coxeter group. And now the different drawing styles basically come in, if, how do I say this? I mean, let me just draw a schematic picture of what the individual Coxeter tile looks like. And it actually looks a lot like the Coxeter diagram, I guess. So, I mean, I'm probably redrawing the same, roughly the same picture, but, and I'm, it's schematic, so I don't have to make the sides of the triangle look curved in any particular way or anything like that. So it's just like, am I doing this right? Let's see, green, blue, red. Okay, and then basically, you can come up with these different levels of detail, these different levels of clutter. We can create a semi-lattice or a lattice of levels of clutter by just considering sort of like a lattice of, I don't know, sub parts or something like that of this tile here or something like that. So what I want to say is, right, there's actually a lot of different ways you do this, but there's a lot of clutter. There's so much clutter that I probably can't classify all the different kinds of clutter, but I just want to classify some of the levels of clutter that you can deal with here. And so like at the top, I could put, how does this work? I want to say something like green, blue, and red. Well, I guess it's like the corners of a cube or something like that, right? There's just like a cube-shaped lattice here, which looks like, I'm doing this right. I'm doing this right. What is it?
It looks good.
Is there anything missing there? Yes, there's this one.
Yes, two things.
Oh, okay. Is that what it is? Okay, that's all I was missing. Okay. And so we have, green, blue, red at the top. And we have, what is it? Maybe green and blue and red at this near the bottom level. And then how does it work? Where's the green and blue? It's like this is green and blue. Sorry. And what, you doing that right? Green and red is in the middle?
Yeah.
And blue and red is over here. And I guess nothing is at the bottom. So I guess the picture becomes maybe completely invisible at the bottom. Well, oh, first of all, right, let me, I still didn't really say how to interpret these levels of clutter. So if a color appears, then you're allowed, then you include, when a color appears at one of these nodes, then you include in the picture edges that omit that color. I mean, that sounds, this is annoyingly backwards to me, but that's the way it is. Maybe there's some better way I could have said it or something like that. But I mean, it's kind of like, right. I mean, I guess what I'm saying is opposite each, opposite the green vertex, perhaps you should think of as a green edge, but the green edge is the one that goes between blue and red or something. And opposite the red vertex is the red edge or something like that. Opposite the blue vertex is the blue edge or something like that. I guess if you think of it that way, then you can just think of it more directly that you're saying you include the green edges, you include the blue edges, you include the red edges, but you just have to have this funny negative definition or opposite definition of what the color of an edge is. The color of an edge is the opposite, is the color of its opposite vertex or something like that.
Yeah.
And So, yeah, so
Okay.
there's like I said, the one at the bottom is pretty degenerate. The picture, I think, just evaporates or something like that. But all 7 of these actually are good ways of drawing the design. You can reconstruct the whole design just from these minimal levels of clutter. So, you know, like if you only draw the green edges and you only draw the blue edges or only draw the red edges, that's enough to reconstruct the whole picture. I should say it's enough to reconstruct the whole picture combinatorially, but that's okay because, you know, we have these ways of taking the combinatorial picture and then realizing it analytically, so to speak. So, you know, when you're using the whole theory to reduce the subject to a combinatorial subject, as Grothendieck somewhat enjoyed teaching people to do, then, you know, you can get away with minimal clutter. But so okay, so there's also, so probably all 7 of these ways of picturing the design are useful. And I occasionally jump from one to the other, and then I say, oh, we just have to, you know, I say something very annoying about how it's really easy. And it really is very easy, but just have to be aware, just have to be aware of, you know, what all these possibilities are. And deal with them. So let's see, what am I trying to say? So if you right, this down here is, this level down here is sort of very useful. This makes the whole thing look like a bipartite graph, a bipartite planar graph. There are these green edges, green vertexes and red vertexes. And there's just these blue edges. The only edges are these blue edges, and they're all going from green to red. So it's, you know, the bipartite is the division of the vertexes into green versus red, and all the edges are blue, and they're all going from green to red. So that's kind of a bipartite graph. And it's a planar bipartite graph because, you know, this is on a plane. So that's one of the ways of picturing one of these designs. And that's very useful sometimes because, I mean, one reason I find that useful sometimes is because I know a lot about, you know, graphs. You can think of them as, well, there's all sorts of interesting graph theory things you can do. And, or if you're a category theorist, you can think of graph, you know, the category theorist's viewpoint on graph theory or something like that. So, but there's also this one up here, which is the lozenge picture. So, right, these two are complementary, right? These are opposite corners of the cube. So it's like you're drawing the exact opposite, the exact complementary part of the edges. And so, yeah, in this case, this opposite corner, we're drawing just the red and green edges. And when you do it that way, then, you know, you've left these holes where the blue edges should be. So it kind of looks like this, what I'm trying to say. It looks like, sorry. It looks like, sorry, wrong color. Right. So, like I say, there's, you know, if you can get even more ridiculous than this and start considering levels of clutter that involve omitting vertexes and stuff like that. I guess at this point, I'm just focusing on the edges and just include whatever vertexes appear as the endpoints of the edges. That's the rule about treating the vertexes, I guess. So, if you Right. So I'm dealing with this green-red thing. So, right. In this case, the omitted edges are these ones right here. Let me make that a color I prefer. Doing that right. What's it doing? Is it thinking? Damn, what the hell? It took so long to erase that it screwed up. Okay, sorry.
Yeah.
I'm drawing this dotted invisible edge. But you should also think of the complementary picture where the dotted lines are the solid lines and the solid lines are the dotted lines. So that's this, two different opposite corners of the cube. And so this thing that I've drawn here, this quadrilateral, that's two triangles stuck together with a red-green edge in the middle, or a green-red edge in the middle, that is, that's called a lozenge. But right, so you can sort of see from the picture that because of these complementary ways of drawing it, the lozenges are actually equivalent to the green-red edges. Because every lozenge has this edge, invisible edge in the middle that bisects it into the two triangles. So you can think of when you're looking at a lozenge, you're really looking at one of these green-red edges. But it's just you have a choice of different ways to draw it, and then if you want to, I actually prefer most of the time thinking of the picture at the top with all the clutter. I kind of like clutter to sometimes. So yeah, like I say, this is just supposed to encourage us to not get scared by all these different ways of drawing the same design, but using these different drawing styles that maximize clutter or minimize clutter. So I'm trying to give myself permission to abuse you in this way that I've already been abusing you, but now I have permission to abuse you.
No, it's good to see the choices laid out. Do you have ever desire to use the 4 methods that you haven't emphasized, which are just sort of like the ones you talked about, but like with different choices?
Yeah, I mean, those are just, those are just matters of permutation of the colors. So it's
it might matter if you're, for some reason, you're get especially interested in poles and zeros one day.
Exactly.
Some other day.
Yeah, I mean, on some days you just, the triptych of infinity, 0 and 1, which is now reminding me of your -1.
Right, I was just thinking of it.
On some days that's just, those are just arbitrary labels, and just you freely permute them. But on other days, you assign mystical significance to, infinity, that's where the poles are, and mystical significance to 0, and then a different mystical significance to 1. And, so I mean, we've kind of mentioned all the possibilities here up to permutation of the colors. But there really are sometimes when you might want to, there are sometimes when you want infinity to be infinity. There are sometimes when you want infinity to be -1, and all sorts of things like that. So yeah, okay. So that was another one of these preliminaries, and now it's almost the end of the time. But that's even if that's all we do today, that's okay, because I think that'll be useful preliminaries. I think I have time to say something interesting about the actual main topic that we're supposed to be getting to, which, as you say, is just following up on last time. So we're really thinking about these designs now. And yeah, okay. So, I mean, we're approaching these designs, we're approaching them in sort of very general ways and very particular ways. And we have to work out some of the general ways to apply to some of the particular ways. So, I mean, there are these very particular, interesting designs that I like. Because I think they might be in the same Teichmüller orbit, and even if they're not, they're probably still interesting. But what do they look like? Those look like the same size.
Yep.
And one of them looks like this. And one of them looks more like what? Like red. Where is it? Like them?
One at left looks like a stop sign that never lets you
Yes.
drive.
Yes. And I'll just put in a little bit more of the coloring here. Again, right. I mean, like I say, I tend to put in as much clutter as possible. So, you know, even though it takes more time and everything like that. So let's see, I'm putting in. And now where do the edges go? It's something like that, and that, and that, 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 and that, and that, 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 that. I think that's what it's like. And this one has what? Doing this right. And then all the rest of them are blue, and then there's like, doing this right. And where do all the, so I didn't quite color in the remaining ones are blue, but pretend that all the remaining ones are blue, then what does it look like? It looks like, yeah, it's like this. I'm doing that. Why don't I remember? Oh, sorry. That last one wasn't really there. It's just that edge there.
Yeah.
And is there any more I'm forgetting here? Like a one there. Hope I didn't forget too many of the other ones. And it's badly drawn. But yeah, so we're interested in these particular designs, and you know, it's all based on the Gaussian integers, and it's based on this. Well, so that right there's this basic algebraic group that's convenient to use here, and it gives us some interesting Coxeter groups. But the basic algebraic group here is the multiplicative group, semi-direct product, semi-direct product, the additive group. Now, I don't even know what the convention is, but maybe it's like that or something like that. Is that the way you would use the?
That looks good, yes.
Okay. So this is an algebraic group. I mean, period. End of statement, right? I mean, we didn't have to specify any particular commutative ring that it's over or anything like that. That's the way algebraic groups work. They're functorial. So this is the algebraic group. But we actually wanted to turn it into an actual real ordinary group by, you know, taking it at the Gaussian integers.
Yeah, probably people would have said algebraic group scheme to emphasize the ring independence. But yeah, anyway, yep.
Very possibly.
It's no big deal. Yeah, I get it.
I mean, I could try to argue for an opposite thing where, you know, you say algebraic group, and then, you know, you have affine algebraic groups. I don't know. I don't know. Yeah, right. Some people might very well call this a group scheme or something like that. So yeah, so these, you know, and you know, this, so what does this one look like? Sorry, looks like so this is a kind of quotient Coxeter group of the previous one. You know, the previous one was kind of universal because it had no constraints on the orders of the composites of the reflections, whereas this one does have these finite constraints. So I think it's something like this. Let's see. This thing here is the rotation group of this reflection group. Well, okay, let's see. Now we're really running out of time. So let me just try to. I mean, I guess what I'm doing right now is I'm just really regrouping for when we'll start next time.
That's fine.
So yeah, there's some really interesting stuff to do here, but we didn't get to it today. So like I say, there's, you know, some general stuff and some particular stuff. These are the very particular designs we're interested in, but we're going to deal with some very general ways of working out Bellyi's theorem, Belyi functions for this for these kinds of designs. And so earlier, some weeks ago, maybe many weeks ago, we dealt with these Shabbat polynomials. So in the genus zero case, or on the Riemann sphere, the meromorphic functions are the rational functions. In very special cases, you can get away with dealing with deal with them being polynomials, like if there's only one green vertex. But here we have many vertexes of each color. So we really have to face up to rational functions rather than polynomials. And that's what I'm going to try to talk about next at the beginning of next time. There's some very nice, I think it's very nice ways of understanding. You know, that, I mean, maybe everyone knew this, but I didn't know this. So I'm really going to deal with the case of rational functions rather than polynomials. And I guess that's where we'll try to start next time.
Okie doke. Yep.
Okay, thanks a lot. I'll see you.
Sure. See you. Great.
Okay, bye.
Yep.